Hello, everybody. Welcome back. We're going to wrap up with transient conduction today. So let's see where we were from last week. So, so we talked about spheres and cylinders and plane walls, and we did an example of transient conduction on the wall of a pipe. And we saw some tricks. The example is example 5.5 of the book. And we saw that some of the tricks, such as considering that the wall was actually, the wall of the pipe was a plane wall. That was one of the tricks, right? We considered constant properties, and we considered the relatively long times, such that we could use only the first term of the series solution. And so up to this point, we saw we saw that the Biot number is one of the key players here. And we have this table, and I'm going to elaborate on this towards the end of today. And what do we see in this table? If the Biot number is much less than 1, say 0.1, then we can do lumped capacitance. If the Biot number is more or less 1, then we have is not much smaller. Not if the Biot number is not much smaller than 1, that means more or less 1 or bigger. Then we have an infinite series, right? And the infinite series on one hand is a pain. On the other hand is using the work, the 4 years of work of somebody else for free. That's pretty awesome, right? Step number 2, after checking out the Biot number, is check out the Fourier number. The Fourier number is a dimensionless time. And if the Fourier number is more or less bigger than 0.2, we can use only the first term in the infinite series. And that was the case of the cylinder, the pipe wall that we saw on Friday. And this is awesome because we went from jumping on a series to using only the first term that becomes a simple formula. Very convenient. And now we not only are saving 4 years of work in which we did not do the PhD to get the equation, but in addition, we can turn the equation into something simple. We went from 4 years to 5 minutes. That's powerful. If the Fourier number is less than 0.2, the infinite series is the answer always. It's just like, although it is the right answer, it's not always the smart answer when we have the right shortcut. But for Fourier less than 0.2, we don't have, as of this moment, a shortcut. In 5 minutes, I'll show you what the shortcut is, because there is a happy life no matter what. And this is part of the power of this class. If the Fourier number is bigger than 0.2, let's call it long times, and the Biot number now is much bigger than 1, we can say that the surface temperature of whatever we're talking about is essentially the same temperature of the fluid, right? And this would be for any shape. We would say the surface temperature is that of the fluid. So what I wanted to discuss today is perhaps one of my favorite topics in this class. And I would like to spend so much more time on it, because this topic is the topic that enables the solutions of really complicated problems in a very practical way. I have done lots of work, lots of consulting using the equations I'm going to show you today. And when we start with convection on Wednesday, you're going to see how we start to recycle the results we generated today. Although we're talking about conduction in the solid, when we talk about convection in the fluids, we're going to see how much of this we can recover. Hint, we discussed from the second week of classes that there's no such thing as convection. We call convection something that in reality is a combination of conduction and advection. So whatever conduction we learn now is a conduction we can use for to study convection. Okay, what is this shortcut I want to discuss with you? It's called the semi-infinite solid. And what is the practical application of it? When we put heat against a surface, however we do it, whether it's a laser beam, we fry it in oil, we put it in liquid nitrogen, whatever we do, doesn't matter what we do on the surface of a solid, the heat is going to take a while to penetrate. Even if the solid is very small, there is a time at which heat hasn't penetrated enough because heat cannot be faster than light, right? So whatever we do, there will be a time at which heat is penetrating. When heat starts to penetrate, it doesn't go very deep at the first instance, right? It can be something huge, and then you see how the heat would take a while. I mean, if it is a sunny day, the heat of the sun is heating up the surface of the earth. But if you're here in Canada, I don't think the Australians know, just by measuring the temperature of the earth, whether it is sunny in Canada or not, because it takes much longer to penetrate through the earth, right? When the penetration of heat is shallow, I don't care anymore about what geometry we have, because the heat penetrated so little that it believes that the surface is flat, right? Some people even believe that the earth is flat, right? Well, we're better than that. We don't believe earth is flat, but we can call it flat very often, and it's going to be very convenient. My table here is flat, or isn't, right? Because for things that are so much smaller than the radius of curvature of the earth, we pretend that the radius of curvature is infinite, and things are indeed flat. So in this case of the semi-infinite solid, right, is much as the case of the plane wall. If the penetration is not very deep, we forget about the curvature if the radius of curvature is much bigger than the penetration. And our ideal model is that of a semi-infinite solid. There is no such thing as a semi-infinite solid. That's a lie. But you know what? So many things resemble a semi-infinite solid that is worth studying it. And if we study this very ideal model, we'll see that it takes us very good places. I'm going to teach you today an equation that my PhD advisor called the $1 million equation, because he made $1 million a year using it. I'm trying to, maybe in a few more years. But it's that important. And it's all based on this semi-infinite solid model, this semi-infinite solid hypothesis. So I'm going to discuss 3 common semi-infinite solid problems, and all 3 will have some similarities. So let's start by looking at this, at how to calculate it. If we have a transient problem, right, we need to use, and the transient is I cannot assume lumped capacitance, and in this case, of course, not, because I'm saying the time is so short that the heat hasn't penetrated enough to make it uniform. So we have to use the equation of heat diffusion. This equation that here has number 41, and it's an equation that we have discussed before, for example, for the case of the transient conduction in the plane wall. You see, I'm talking about a semi-infinite solid today. I was talking about a plane wall last week. 2 things are very different. One thing is the wall of this room, and the other is the surface of the earth, right? However, we start with the same equation. This innocent looking equation, as I mentioned last week, is everything but innocent, because the trick of this equation is in the boundary conditions. So this says very little, but the boundary conditions say a lot. This is a linear equation. This is a homogeneous equation. This is a partial differential equation. This equation has two independent variables that are space and time. This equation has one dependent variable, which is temperature, that depends on space and time. And so in this equation, it's embedded the simplification that thermal conductivity is constant. Otherwise, I couldn't write the second derivative. It would be a more complicated expression, which we saw on week 4. And I need then one initial condition for time and two boundary conditions for space. So let's go one at a time. In this semi-infinite solid problem, we need to use our imagination. So we imagine something that is flat on the surface and deep, right? What could be a really, really thick wall. And we said that at time zero, all this very, very, very thick wall, this semi-infinite solid, is at temperature T0, right? Let's say 20 degrees C if we wish, something like that, is at uniform temperature. Then this will be our initial condition. The two boundary conditions, what are those gonna be? One boundary condition is that if we go very, very deep, far away from where the heat is affecting it, the temperature and X equals infinity, right? Really, really deep in, at any moment in time, the temperature is T0 too. This condition essentially says, if you go deep enough, the solid has no idea of what's happening in the surface. So initially, we're at T0. Deep enough, we're at T0 all the time. And here, see, innocent looking equation with innocent looking boundary conditions, two of them. And then here comes the kicker. What's the third boundary, the second boundary condition in space? And that will be the condition on the surface. There are many possible conditions. I'm going to discuss with you the three that are in the book. Maybe to the future I can add more because this is so useful. So there are three possible boundary we're going to discuss three boundary conditions. We can choose only one, right? We already have an initial condition. We already have one of the boundary conditions. And now for the second boundary condition, we have three choices based on as we follow the book. Choice number one, we are going to say that the surface of the solid is at a constant surface temperature. So we're going to say at time equals 0, the temperature of the surface is Ts. I impose it. For example, that would be the case if I have a very, very, very intense convection and it takes instantly the surface temperature to the value of the temperature of the fluid, right? So this is a potential condition, which we're gonna see soon. Option number 2, let's say that this boundary condition on the surface is that of a constant heat flux. And that means I'm imposing a heat flux. And because if you remember when we looked at differential control volumes, if I make a differential control volume just on the surface, I would be able to say that all the heat that comes in is the same as the heat that goes inside by conduction. That's why we have Fourier's law here. It says Fourier's law is this Q double prime naught, that is the heat that is imposed on the surface. This condition, this is a condition you have, for example, if you have a laser beam hitting a metal. I just very recently finished a consulting gig in which I was using exactly this boundary condition to model laser heat treatment of components for oil and gas. And you know what? It works awesome. Works awesome. We compare that with many measurements. You'll be blown away how well it works. This class is not Mickey Mouse, it's a real thing. So this is condition number 2, right? Constant heat flux. What is the surface temperature? I have no idea, I'll tell you later, but I know I'm imposing heat on the surface because I'm shooting it with a beam. Or for example, you're on Earth and the heat of the sun is coming. That heat is imposed. It's more or less 1 kilowatt per square meter, right? That radiation from the sun, right? That is this boundary condition here. A third boundary condition, which actually is one that has a little bit of more generality, is how about if we have convection on the surface of our semi-infinite solid, right? Now the boundary condition looks a little bit more tricky because it says conduction, right? This Fourier's law here says conduction at the surface is x equals 0, is the same as convection on the surface. Convection boundary condition. I'm going to discuss all these three and see a little bit more what they are. So let's discuss, to start, case number 1 of constant surface temperature. And here things got interesting. I've been telling you all along how we write down the equation, and then we are lucky that we're saving 4 years of somebody's PhD thesis who solved it, right? And then I typically tell you, I used to teach this. Up to this point, I used to teach all these things. All the things we're not doing, I can do. Except that now we're getting into the point in which I don't know myself how people solve these equations. Thank God we're engineers and not mathematicians, right? And guess what? We still have a solution. So maybe this guy took more than 4 years to do it. I don't know, but the bottom line is we have a solution. If we have a boundary condition of constant surface temperature, the solution to this equation is this one in equation 45. It says temperature that depends on space and time is initial temperature, it always starts like that, plus Ts minus T naught. This is the jump between surface temperature and this initial temperature, times this function here, this ERF, that sounds like as if somebody's choking, right? This is the complementary error function. It sounds like a mouthful, right? So I'll tell you 2 things about it. Number 1, that a complementary error function looks very much like a decaying exponential. It's not, but looks very much like it. Number 2, I'm going to tell you, it's in Excel. It's amazing. Just like what we talked, that the Bessel functions are in Excel, they are not in your scientific calculators. I've never seen a scientific calculator with Bessel or error functions. Error functions, yes, because it's a statistical function. But Excel has it all. It's amazing. Of course, MATLAB too. So you have this error function of x over 2 square root of alpha t. Whatever this is, I want to draw your attention to something. The argument of a function is dimensionless. So we have x with dimensions of length, that is depth, and this is square root of alpha t. The square root of alpha t has also dimensions of length. As we talk about transient conduction, you're going to see this square root of alpha t appears all the time. So don't do anything in particular right now, but I want to put into your memory that square root of alpha t is the character we're going to see many times coming up in this novel. Okay, and so here we have a graph of what this error function looks like. The vertical axis is error function. The horizontal axis is this psi, and by psi, I'm using this as a shortcut for whatever is inside here, right? And if you remember from when we were doing lumped capacitance, in which we had an exponential decay, the decay had a characteristic length. The characteristic length of an exponential decay is 1, right? If we say e to the minus x, the characteristic length is 1. But in this case, the characteristic length of an error function is square root of pi over 2. Somehow, this is true, right? But this, guess what? It's more or less 1. It's 0.89. It's very similar to an exponential, right? And this is the exact number, square root of pi over 2. And this is our characteristic value for the error function, complementary error function, which means now we can define a characteristic penetration of heat. So if I take this, this was just error function, and this is a graph down here, a graph in which I have temperature versus depth under the surface. The coordinate x is the depth under the surface. X equals 0 means surface. And we see some sort of a decay. Number one thing, most important thing to say here is this graph that looks so much like the exponential decay in lumped capacitance is very different. In this case, this is x, space, is not time. In a lumped capacitance, we saw an exponential decay in time. Here we see an exponential decay in space. Of course, the graphs look very similar, but if you mix space and time, you either don't know what you're doing or you're Albert Einstein. So if you're Albert Einstein, tell me, because then I have a couple of questions for you because of things I myself don't understand. So in this, if we see this error function, x over 2 square root of alpha t, right? This is a characteristic decay, and when x over 2 square root of alpha t equals this characteristic value, I can use this relationship to determine the characteristic penetration of heat, right? Same as we did before. This is our characteristic value. And I do this characteristic length, xc over 2 square root of alpha t, right, is what I have here, this argument of the error function. And I said this is square root of pi over 2. Yeah, this is the magnitude at which the error function has its characteristic value. If I set this up, then I can solve for xc. And xc is 1.77 square root of alpha t, right? It would be a square root of pi here, which is more or less 1.5. Take home message of equation 48. 3 things. Number 1, the characteristic penetration of heat is more or less square root of alpha t, is proportional to square root of alpha t. Remember that I said I'm planting an idea in your mind about this square root of alpha t? It started to appear already. So the characteristic penetration, the penetration of heat is proportional to square root of alpha t. More time, more penetration. You know that. Of course you know that. The one thing that might not be so obvious is that as time goes by, the penetration increases, but every time increases a little bit slower and slower and slower because it's a square root. Number 2, this characteristic value is 1.77. Don't memorize it. I promise you 1.77 is appearing again later this week or next week when we discuss convection. This 1.77 is part of the exact solution to the Navier-Stokes equation. You're going to see that later. So this is a cool number, and it's 1.77 is just the square root of pi. And number 3, this 1.77, I'm going to call it more or less 1.5 because I'm going to show you other things that might come in handy, right? This is $1 million equation. If you, the fact of that we can anticipate the penetration of heat depending on time means we can cut through this partial differential equation in a very reasonable way, in a very cheap way, because square root of alpha t I can do pretty much in a 4-function, well, in a 5-function calculator, those that have a square root 2. This equation, just like I said, this equation looks innocent, equation 41, but it's not. This equation that looks so simple, xc equals 1.5 square root of alpha t, looks like nothing. It's everything. That equation helps us cut through the partial differential equation without solving it, this formula here. Okay, so for example, now we can say, if the surface is always at the same temperature, how much heat is coming into under the surface? Okay, I can do the boundary condition, right? With I can do Fourier's law on the surface, k over dt dx. But guess what? dt dx is delta t, right? And because we were doing the tangent, would be over this characteristic value. And I'm using here the exact value. And all of a sudden, I didn't even need to write the derivative. Because we were using a smart characteristic value, I can anticipate this gradient of dt dx as delta t over xc. And now I have a formula so easily. And this formula tells me how the rate of heat coming into my semi-infinite solid. And what does it say? That the rate of heat decreases with time, of course, because as heat is penetrating, the gradient is every time more and more shallow. And if the gradient is shallow, there's less driving force for heat to come in, right? And eventually the heat, if at long enough times, the heat becomes very small. So this I went over very quickly. It's extremely important, and it's much more difficult than the way I said it. So please take a look at the notes. Please put this in Excel and think about it. This formula here is gold. Somebody solved it for us. I don't even know how they got it here, but they did it. And this helps us predict the temperature at any point, at any time, in a semi-infinite solid that sees a temperature jump that is maintained. Can be heating up, can be cooling down. Okay. Case number 2. How about if we have a constant heat flux on the surface? So we irradiate it with a laser. Now the equation, again, this is a solution, equation 51. You might say, oh my God, look at all the ants crawling. Yeah, just think of how the hell, I have no idea whatsoever, how somebody figured out that this is the solution to the partial differential equation. Somebody took 4 years in doing this in a PhD. To me, it would be a lifetime. But for us, because we have this solution, it's 5 minutes. Plug and chug. Now, every time there are more and more things to plug in, right? Q double prime 0 is the heat flux into the surface. Alpha t, see how alpha t appears all the time? And this is in a square root, right? Square root of alpha t here, square root of alpha t again. So we're good old friend. It's always appearing, right? Alpha t, square root of alpha t is essentially our depth of penetration of heat. Now, if I say x equals 0, I would get the temperature on the surface. And so this equation 51, when I replace x by 0, right, this term goes away. This term here, exponential of 0 becomes 1. and I get this value for the surface temperature. And what do we see? That at time 0, the surface temperature is T naught, and as time goes by, the surface temperature increases. And of course, otherwise, how can I weld anything? I have to zap it with a laser, and after waiting for a while, it melts down. And this is a reason why if you move the laser too fast, you don't weld anything, because you don't have enough time to stay over each point until so the temperature raises and reaches melting, right? So if we have a constant surface, a constant heat flux on the surface, here we have the solution of temperature at any place at any time. And for the surface, here we can calculate the surface temperature. This is super awesome. If I were to do the derivative of this, which I did it myself, but now it's easy because I have the solution, I can calculate my penetration of heat, right? Doing a similar business to this one, except that now it's not error function anymore, it's something much more complex. I did it, and we can have that the penetration of heat now is something proportional to the square root of alpha T. Square root of alpha T again and again and again and again. We'll never get away from that. But if we know what it is, it's going to be awesome. So here we have the square root of alpha T, and the factor now is this 2 over square root of pi, that is 1.128, right? It used to be 1.77 for the case of constant surface temperature, and this is 1.128. You know what? I'm going to call both 1.5. If I tell you to get the exact number, you use the proper exact number. But 10 years from now, chances are you forgot about everything. But I hope that when you see square root of alpha T, say, ah, yeah. And how much square root of alpha T? You can call it 1.5, and you're going to be awesome. You're going to see some people call it a factor of 2. Some people call it a factor of 1. I split difference 1.5. Really, it's not such a big deal. The real big deal is remembering that penetration of heat has been proportional to square root of alpha T, give or take 1.5, for 2 very different boundary conditions, either constant surface temperature or constant heat flux. And here we have like what the evolution would look like. Here we have depth, right? This is our semi-infinite solid going to the right. We have our laser beam or our light of the sun hitting on the surface, and the temperature starts to increase. At the same time, the heat starts to penetrate in. And this penetration that was 1.128, right? Square root of alpha T, and the surface increases. And this gradient is interesting. If you remember the gradient, the gradient meaning the rate of heat flux into the surface used to decrease for the case of constant surface temperature. But now this gradient is constant. Why is it constant? Because I'm putting a constant amount of heat into the surface. And the third case I'm going to discuss briefly, but it's the case of surface convection. This is the third case I wanted to discuss. There are many more. And now we have the solution, and I have even less of a clue of how somebody figured out that this is a solution for the constant, for a convection boundary condition. This is awesome, for example, if you are you're cooling something with jets. Way before I went to study in Boston, I used to work in an R&D center in Argentina, and we were applying graphite lubricant with a spray, and the water evaporates and the graphite stays in place. And I explored how to calculate the temperature evolution of that process to make sure we were not boiling the water too early or too late in the spray. And I put this equation from this same book we have, was a much older edition, but I put exactly this equation, and I put a thermocouple in the experiments, and this was amazing at calculating the heat transfer and the temperature evolution that I was measuring. I was surprised how good it was, right? So the equation looks complex, but works. And again, every time you think this equation is complex, think how much luckier you are that you did not need to derive it. And what can I tell you about this one? It's an interesting thing. So for the convection case, at the beginning, right, the surface is at the initial temperature, and you're extracting heat, right? And the heat flux is H times delta T. That would be T of the fluid minus T of the surface, right? And initially the surface is at T naught. So at short times, this equation behaves like the constant heat flux equation. At long times, the surface temperature pretty much reaches the same temperature of the fluid and starts to behave like a constant surface temperature equation. How interesting. So this equation is kind of a hybrid. The convection boundary condition is like a hybrid of the previous two conditions we discussed. But you know what? The penetration of heat in this case, which is much more complex, is still more or less 1.5 square root of alpha T, because however you look at it, is more or less 1.5 square root of alpha T. So from looking at these three boundary conditions, the take-home message about this is no matter what I do to the surface, heat penetrates more or less 1.5 square root of alpha T with any of the boundary conditions we know. And the ones we don't know, let me tell you, it also penetrates 1.5 square root of alpha T. I've been trying to come up with a demonstration of why this is so. I haven't been able to do it yet, but this is something I hope to do someday before I die, because it's so cool that such a complex problem in such incredible diversity of conditions, whether it's a laser or boiling in an oil, always the heat penetrates the same. So I put all this in the notes as well as I could. I put a lot of love here. So take a look at what we wrote here. The book also has it. Now, we said that nothing is semi-infinite. That doesn't exist, it's a lie. But we said this very often is a really good approximation. So the question is, when? When is it a good approximation? And it's a good approximation when we say that the solid is bigger than the penetration of heat. So if this is the surface of my semi-infinite solid, and this is inside the semi-infinite solid, if the heat penetrated up to here, let's call it twice as thick. If something is twice as thick as its heat penetration, I'm going to call it semi-infinite, because at twice the distance of penetration, it does nothing changes anymore. I can keep going and going, and it's not going to make a difference. So if the penetration of heat is 1.5 square root of alpha T, give or take, I'm going to give it twice that value. I'm going to say something has to be thicker than 3 square root of alpha T. This is an engineering approximation, but happens to be pretty good. And if I write this in the form of the Fourier number, if you remember, was alpha T over L squared, right? Alpha T over L squared, that is a Fourier number, that would give us 1 over 3 squared, that is more or less 0.1. So I've been talking quite a bit about how heat would penetrate under a surface. And we said, okay, the surface has to be twice the thickness of this, whatever we're talking about, has to be twice as thick as the penetration of heat. Because the penetration of heat depends on time, that means for a given thickness, there is a maximum time at which we reach the halfway of heat penetration. What is that time? The time that corresponds to Fourier of 0.1. So, funny enough, does a semi-infinite solid exist? No, it doesn't. Can I say that something is semi-infinite? Yes. Can I say that, I don't know, that this sheet of paper is semi-infinite? Many of you would say, oh, it's so thin. And you know what the answer is? Yes, of course. It all depends on the time constant. If something is semi-infinite, depends on the time constant. If the time constant is small enough, then if this time is very small, this thickness can be very small. This is not intuitive. People think that thin is thin and thick is thick, but heat doesn't think in those terms. Heat thinks in its own terms about the time it would take it to get someplace for a given time. And if you give it too little time, it's gonna think that something is infinitely long. Another interesting thing, we can now calculate the thermal resistance of a transient. Thermal resistance was a concept we have used for steady state. However, we can extend the thermal resistance of a wall to say, how about if the resistance of a transient is this thickness, that is the penetration of heat, this xc over k, right? Same as the r double prime of the wall per unit area, resistance per unit area was L over K, and L was the thickness of the wall. Now we would say this is the penetration of heat. And for the case of for the case of this constant surface temperature, we would get this formula for resistance. See the square root of alpha T again? There is no escape. Or 1.13 for the other boundary condition. You know what? As a ballpark term, in general, we can say the resistance of a transient, thermal resistance of a transient, is 1.5 square root of alpha T over K. I was using exactly this 2 weeks ago for a job with Syncrude, calculating a new technology they're evaluating. Exactly this formula of thermal resistance. I was using the one for here, for constant heat flux. This is for real, guys. This is awesome. Please learn it and make money, or at the very least appreciate that you could if you wanted. In these last 5 minutes, I want to go over a case that I think is so cool to discuss with you. That is the case of a deep fried ice cream. So I don't know if you're familiar. To me, this was new. I don't even know how I figured it out, but it was for this class that you can deep fry ice cream. Now, funny enough, because deep frying is definitely above 100 degrees C, but ice cream is definitely below 0 degrees C. How can this be? So I found a recipe on the internet that is here, and I haven't tried it myself, but I'm sure it works. If any of you tries it, I'd like to know. And the recipe says, put your ice cream in the freezer for 25 minutes. So let's do the heat transfer of this. If let's say the scoops of ice cream are 6 centimeters in diameter, right? We can calculate the Biot number, and the Biot number is 0.5. What does it mean? It means that I cannot assume lumped capacitance. I calculate the Fourier number for 25 minutes, and is bigger than 0.2. That means if I want to calculate the evolution of my ice cream when I put it in the freezer, I can use only the first term of the series to calculate it. Anyway, that's putting in the freezer. That's not where the fun is. The fun is when we say, according to the instructions, that we deep fry the ice cream ball for 6 seconds. So first we have to put a coating of the breadcrumbs, right? To make it like, what is the term? I don't know what the term is, but you have to do the egg wash and put the breadcrumbs on top. And then you deep fry it for 6 seconds. Let's look at the numbers now. When you're deep frying, I think we have a bit, I think the number is 10,000. When you're deep frying, this heat transfer coefficient would be 10,000, even if it is 1,000. We get a value of BIOD of 500, much bigger than one, right? Okay, that's cool. And what is the Fourier number? The Fourier number is 0.001, much less than 1. So at these short Fourier numbers, right, not only I could not use the first term of the series, I would need to use the complete series, or I can use the model of the semi-infinite solid, in which the heat will try to get into the ice cream scoop, but in the 6 seconds we have, it just has a very small amount of penetration. So because the BIOD number is so high, we're going to use the model of the constant surface temperature, which actually is convenient because it's the simplest one. So it tells me, let's calculate what the penetration of the heat is into the ice cream, right? And it says that penetration of the ice cream would be the penetration of heat into the ice cream is 1.68 millimeters. You know what? That's the thickness of the breadcrumb layer. This is a reason why we can put ice cream inside the deep fry pan, and what we get out of there is ice cream again, and not nothing, and we didn't dissolve our ice cream in there. This is awesome because now we can understand how this paradox of ice cream being below 0 and frying being above 100, how they can coexist. Yeah, they coexist, but for 6 seconds, and because it's protected with the egg wash and breadcrumbs. I use, in this case, the exact formula, that is 1.68 millimeters. If we have used the 1.5, that is approximate, I would have gotten 1.42, that is very similar. Everything we have discussed so far is in this table here, and tells you want to use long capacitance, or want to use the first term of the solution, or want to use the semi-infinite solid. Is 150. I'm going to stop here. With this, we wrap up transient conduction. I'm going to take a 10-minute break, and then I'm going to be back here for office hours. Thank you very much. I'll see you soon. Bye-bye.